Welcome back. So last lecture, I told that we'll start with a new topic. So this is a new topic on plate tectonics in particular, and in this we'll try to understand that how this uh, crustal deformation takes place because of the plate movements and how the mountain building activities are been seen in context with the ongoing deformation and the deformation which initiated long back actually during the geological time period and its implication towards the earthquake hazard. So if you look at this picture, this is a beautiful photograph of the Haldar range, photograph that is your higher Himalayas clicked from Kangra Valley. So this mountain definitely it looks very beautiful, but it has gone through a number of phases of deformation, and the plate tectonics plays an important part in this. So, what is plate tectonics and how it came into discussion, and then what we are having the understanding at present. So that part we will try to look into that. Okay. So about the plate tectonics, as we discussed about the tectonics, that it talks about that how the deformation took place on regional scale or global scale, and then site specific scale or local scale. So mostly the plate tectonic, if you look at, then it is the movement of plates and the forces acting on them. So how the plates are moving and what are the forces and at what rate the forces are been acting on these plates, and what is the outcome or the end result of this forces which are acting on different plates. Okay. Then it also explains us the distribution of volcanoes, the the distribution and the occurrence of the earthquakes, fault, folded mountain chains, rock assemblages, and seafloor structures. Okay. So the question you may ask that how this rock assemblages comes into this picture, because this is again related to the plate movement, and the rocks which are forming uh, underneath or we are seeing at the surface are the result of the plate movements. Okay. And of course it talks about the distribution of the earthquakes and all that, and part of this I discussed in the that how the earthquakes are seen distributed aligned along the plate boundaries. Okay, so now things will be more clearer to you people, where we are talking about that what are the plate boundaries, how we classify those plate boundaries and all that. Okay, further, the forces that drives plate motion arises from the mantle convection system. Okay, so this is another aspect which usually we try to look into, that that what are the reasons for this motion of the plate and all that. Okay, so for this usually what we look at the interior of earth, but as I was talking about that there are the cycles, we say rock cycle or tectonic cycle or hydrological cycle, they are all interconnected. So for example, if we look at the that what is the relation between the tectonic cycle and your rock cycles, then we say that okay fine, that the the rocks which are been pushed down into the interior of earth, they will start melting, result into the magma formation, and this magma is either in or act as an intrusion to the crust, or they will result into a volcanism. Okay, and that will result into the formation of the igneous rock, that is what usually we call volcanic rocks, and then you have the ongoing deformation will result into the uplift, which gives you the mountain building activities, and then through weathering of these mountains or the portion of the crust which has been uplifted, okay, that what we call the continental crust. So the weathering process will result into the formation of the soils or the loose material we call alluvium. So this is through the erosion and deposition that will result into the formation of this loose material, and then you have, so those loose material is there, and then if they solidified, they will result into the formation of sedimentary rocks. And if these sedimentary rocks are subjected to high temperature and pressure, they will result in the formation of metamorphic rock, and again the cycle goes on. Okay, so it is, this whole cycle is interconnected with the tectonic deformation also. So this again try to explain the rock cycle and also its relation with the hydrological cycle. And one point which I mentioned in the last slide about that what was the advantage and what advantage we got because of the development of Himalayas for the Indian subcontinent side. Okay, we'll talk about that, and we also already I spoke about this part before also. Now coming to the interior of Earth, uh, of course we are going to discuss about different units when we are talking about the seismic waves and all that, but briefly we'll touch upon the overall what is the property of different layers of the earth. It is not homogeneous. It has different like it varies from chemical composition, from and the physical properties also. Okay, physical like it is not the solid everywhere. At part it is liquid, and some places it is semi-solid also. Okay, and the composition also varies from as you move from the surface, that is your crust, to the interior of earth. Okay. So broadly, if we see, then it has been like you have the crust, then mantle, and the core. Okay, if you look at this section of the interior of earth, you have, as I told, that you have crust, which is the thinnest portion of the earth, topmost one, hard, and then you have mantle here, where that mantle, the upper portion of the mantle is your partially liquid. That is what we call asthenosphere, and this asthenosphere is responsible for generation of convection currents because of continuous heat flow, and that results into the movement of your uh, plates. Okay, where we classify these plates as an oceanic plates and the continental plates. So thickness also has been given here, that what is the thickness usually, the average thickness, it varies around the globe. Okay, so it is almost like you are having 20 to 70 kilometers of crust in some places you will see. Okay, now very interesting part, which again I would say that we will discuss that this when we are talking about the seismic waves, because seismic waves uh, travel through some layers, don't travel through some layers actually. So, and what are the reasons for that? Okay, but the important part for us in this course is to know that, okay, what which layer is responsible for the generation of convection currents and driving the plates. One is the asthenosphere. Okay, so this is what has been shown here with this figure to explain that you have the continuous generation of heat, and to some extent the mantle plume, and then because of the convection currents which have been developed here, the plates, what we call the oceanic plate and the continental plates, or the continental crust or oceanic crust, they are forced to move, and the motion is been generated because of this. Okay, now before we get into the details of this the formation of like the motion of the plates and all that. Okay, let's see this example of isostasy. Okay, now isostasy is the principle of basically it governs the rise or subsidence of the crust. Okay, until it is buoyantly balanced. Now this buoyancy is because of what? Because of the all the crust, as I told, that they are they're floating, either it is oceanic crust or the continental crust, they are floating on your asthenosphere. Okay. So if they are buoyantly balanced, then we call that this plate or this portion of the earth is under, like it is following the principles of isostasy. Okay. So isostasy, because what happens is that if you try to remove some portion of the crust, okay, like if we all simple example, if we take that we have an boat or the steamer which is floating on the water. Okay, so some portion is at the under the water, and then some portion is exposed. Okay, again that depends on the weight, the density of the material. Okay, and the what we can say the density of the liquid on which it is floating or it is, so that is important. So if you, like for example, if you load the boat, then it will sink a little bit. Okay, but you so if you unload it, it will come back. Okay, so that is exactly what is happening in terms of the isostasy. It will try to balance itself. Okay, so this lithospheric plates also, which are floating on the asthenosphere, they will try to balance itself if there is any sort of an removal of the material or adding up of the material there. Okay, because of isostasy, all part of lithosphere, this is we are talking about the like oceanic plate, and you are having continental plates. Okay, or oceanic crust or continental crust, they are floating in an equilibrium manner. Okay. So low density, for example, this is we are talking about the wood, but we will come to the earth crust, the continental, and the importance of that also we will later realize. Okay. Now low density wood blocks float high and have deep roots. Okay. Whereas the high density blocks float low and with the shallow root. So for example, if you take this one, keeping this in mind that you are having the low density, so low density blocks float high, deep roots, and high density float low, shallow roots. Okay. So that means the uh, the lighter density crust, or you can say the crust with the lighter density, will float high and will have deeper roots. Okay. Whereas the high density crust will float low with shallow roots. Okay. So let's see this one. This is an example of your wood put into the water with an heavy and light weight. So if the low density, that is the low density, the lighter wood block floats high as compared to your heavier block. Okay. So this is flowing high. Of course, the area and the mass is also important. So this is floating high, as well as the root of this. Okay, that is the heavier one, is not much. Okay, it is shallow. But if you see the root of the light one, it is much deeper. So same thing goes for this iceberg also, where the height to which a floating block of ice rises above the your water depends on the density of water compared with the density of the ice, because that you have to take into consideration. So the density of the water compared to the density of the ice, the material, what is the density of the material and what is the density of your material on which it is floating. Okay. So for example, water freezes. When water freezes, it expands to become a low density, as ice density is around 0.9 G plus cubic centimeter, relative to liquid water at 1 G, okay, per cubic centimeter. Thus 90% of an ice cube, okay, will be underwater. Similarly, for the larger mountain ranges, approximately 84%. So, this is an example of your iceberg. So, you are talking about the ice which at 90% will be submerged because of the density, because the ice is having 0.9, okay, gram per centimeter cube, and so, and this is also, so this, and this is around, it says around 1, okay. This is the ice, and then the liquid water is around 1 gram per centimeter cube. Now, similarly, if you take in terms of the crust, okay. So, 90% of this is for the iceberg, but this similarly if you take for the mountain ranges, 84% of the mountain of continental rocks, okay. So, continental rocks usually will range in, with the density will be something like that, okay, 2.7 to 2.8 G, that is gram per centimeter cube, will submerge into the mantle having the density of 3.2. Okay. So, this is 3.2 and this one is having your 2.7. So, it says that around 84% will be mountain range or the continent will submerge, okay, and 15 or 16% out of that 100 will be seen floating up, okay. So, everything depends on that what is the density of the material on which crust is floating and what is the density of that particular crust, okay. Because all crust, both the crust like oceanic and continental will not have the same density, okay. So, now coming further, if you look at this, so what was the density which we are looking at? 3.4 to 3.5 of mantle, that is this one, okay. Mantle is having around 3.5 to 3 or 3.2. So, the oceanic crust, if you look at here, is bit heavier, denser as compared to the continental crust, okay. This is 2.8 and this is around 3. So, these are the two crusts, oceanic and continental, which are floating on mantle, which is having around 3.4, okay. So, here you have this one is denser, okay, less denser, continental crust floats on denser mantle, okay, because it is so mantle is much denser than this, okay. And here you are having continental crust is less denser than the oceanic crust, okay. We are just trying to look at this around 3 and this is around 2.8, okay. So, what we learn from the previous two slides is that your lighter one, okay, lighter ones will float higher and the heavier ones will float low, okay. Always, as well as the lighter ones will have deep root and the heavier ones will have shallow roots, okay. So, this is absolutely correct for that, okay. So, the continents, that is landmass, okay, what we are having, they float high because they are made up of rocks with lower density than the rocks of the mantle or the oceanic crust. So, this will float high and will have deeper roots. So, if we look further with this understanding that what we are having in terms of the um, the lighter crust and the heavier crust, and then the density of the mantle. Okay, so you will clearly look around the globe, that there are places where the continental crust are floating much higher, and best example is Himalaya. So for Himalaya, we will have deeper roots. Okay, and we have it floats higher also. Okay, also. So isostasy, if we further look at that, what is happening if you uh, relate it with the crustal deformation, then the horizontal compressional forces will cause shortening and thickening of the crust. Okay. So what you see here, that this topography will also develop. Okay, and at the same time, because of this ongoing deformation. Okay, at the same time, you will also see that this portion is getting uplifted, and, and you are also having the sagging and subsidence over here. So this will result into the thickening of crust. Exactly similar process is going on in Himalayan region. Okay. So we are getting thicker, deeper roots and taller mountains here. Okay. Now isostatic adjustment. So what we have learned is that if you are having lighter, deeper roots, taller exposure, heavier, shallower roots, and shallow exposure you are having. But if you remove some material from that, I gave the example of the boat, and that if you load it, it will sink down a little bit, and you unload, it will come back. Okay, so that will be some change in so exactly if you are having the floating conditions of this continental crust. Okay, of course you have this thicker crust which is available, but you erode it. Okay, so erosion will be there. So if you keep eroding, then what you will have is that this was the previous, this line, okay, of the bottom root. This will come over here. So there will be an uplift here. So this uplift is because to maintain the isostatic balance. Okay. Later, if this continues and no more tectonic deformation is going on, or the tectonic deformation is slow as compared to what erosion is going on, then it will erode the area very fast. Okay. And the time will come, you will just see that this portion is removed. Okay. So this is the previous one. Okay. So now what we see is the flat surface. So as weight is removed from the top by erosion, the crust rebounds upward. So this is the rebound which is taking place. Okay. So this we also call isostatic rebound. The process of erosion and isostatic uplifting will continue until mountain block reaches normal thickness. Okay. So this is the normal thickness which it had. Okay. So it will keep on, like erosion is going on, so it will keep on bouncing up till it gets the original thickness or normal thickness. Okay. So no more root is available further down here. So no topography on the surface will be seen. Eroded sediment can result into the subsidence because you are loading this material which has been coming out of this area somewhere else. Okay, or you are loading this on either side here. Okay, so this portion will experience subsidence because they are getting loaded with that. Okay. So those adjacent areas will subside. So if you look at this example again over the time period, and same process what we were talking about starts. Okay, so you have an isostatic uplift to bring back this area in equilibrium, isostatic adjustment and equilibrium, and then finally it stops when it achieves or acquire the original thickness. Okay, and the landscape will change from mountains. You will have uh, the still mountain continues, but this part the elevation was much higher. Okay, then low elevation, so you start looking at the vegetation coming in. Okay, and then final where there is no additional crust portion is available beneath or subsurface, then it will be like putty plain. Okay, it will be completely flat area. So we usually look at that how things got evolved. There are acceptable theories about that how earth evolved, and earth when the earth was formed, okay, 4.6 billion year ago, that was your the the birth time of the earth. Okay, then there were number of events like supernova and big bang that resulted into uh, the process which started, okay, uh, within the earth. So this spiral figure, it shows the time scale right from Precambrian, then Paleozoic era and Cenozoic era, and different epochs related to that. But before the epoch, we see period. Okay, so you have like Cenozoic era. If you take, then you have like within this you have tertiary period and then quaternary period. Quaternary period is further divided into two, that is your Pleistocene epoch and the Holocene epoch. So you will see that the Pleistocene was the time mostly when the human came in, but industrial revolution was during the Holocene epoch. Okay. Now there are few facts which one should remember about that how the age of the earth was when we came to know about it. So this age was like it is 4.5 to 4.6 billion years. This age was determined through radiometric dating of uranium thorium by using mass spectrometer. Continents, if we take, then we have 30 percentage of the area on this Earth's surface is been occupied by oceans, continents, and 70% is been occupied by ocean basins. Okay. Then we have also the sea level changes events which have occurred through time. That is what we look at in terms of the glacial fluctuations. Prominent features of the the continents are linear mountain belts, okay, alpine Himalayan belt. Highest peak point on Earth is your Mount Everest with 8,850 meters of elevation. Okay, and then you have prominent features in ocean like ocean ridge system continuous belt of which is covering a distance of around 65,000 kilometers. Then the lowest point on the earth is the Mariana Trench, 11,035 meters. Deep sea trenches are subduction zones. Okay. So in short, what you see here is the distribution. You can say that okay, fine, distribution is fine, but the highest point and the lowest point on the earth This is basically result of your plate tectonics. So this part we have already discussed, so let us move ahead. This is again showing that how high will be your continental plate and the oceanic plate. So as I told that the plate movements started way back before in 225 million years, okay, back. And how it moved, there is a cartoon which we would like you to go through and see, and that talks about somewhere over here. Okay, but before that, we will see about a few facts about the plate tectonics. Okay, so earlier, this gentleman, Professor Alfred Wagner, he gave a theory of plate drifting. Okay, and he said that this continents are like if we play jigsaw puzzle, then we try to connect uh, the cards here, and then we say that okay, this is exactly fitting in this the boundaries and all that. Okay, so Alfred Wegener initially he gave a concept or the theory of continental drifting. That means the movement of the continents, okay, from its present location. And then he looked at the boundaries of South uh, America, and you have South Africa. So these boundaries looks like that they will exactly fit into one another. Okay, and that's how the thought process started about the continental drift. The continental drift was like, for example, if you're having those continents together here, they cracked, fractured, and then they started moving in their respective directions. No solid, or we can say preferred path was been created. They moved randomly. So he told that there is the high possibility that these continents were together in long way back in 50 million years back and all that, but they they moved after that. Okay, so this is what he suggested was that all the continents, and in particularly India, we for us we can say that so it was located close to your south pole, so far away from the equator. But now what we see, the India is in northern hemisphere. Okay, so they said that this probably was the configuration of different plates, considering the outer boundaries and all that. Okay, because this is in South Africa and America boundary here. So they term this as an land Pangaea, and the southern part, okay, of this was also termed as Gondwana land. So this is what has been shown here. That is, you are having Laurasia, and then southern part you are having the Gondwana land. Okay. So with this, we'll stop here, and we'll continue with more details on the plate tectonics in next lecture. Till then, thank you so much. Namaskar.